Hi, my name is Jialin Li, and I'm an assistant professor in the School of Computing. Today, I'm very excited to talk about some of the research I've been working on recently. First, let me take this opportunity to thank the organizers for inviting me to this research week. Hopefully, you guys will find this talk very interesting. So I'm generally work in the systems area, including operating systems and distributed systems. In this talk, I will share with you some of my experience and thoughts on the system design in the post-Moore's law era. So a little bit about myself. I did my undergraduate studies in computer engineering at the University of Michigan. After I got my bachelor's degree, I went to grad school at the University of Washington, working with a number of faculties in the Department of Computer Science and Engineering. After that, I became an assistant professor in the School of Computing earlier this year. The Moore's law has fueled the semiconductor industry for the past 50 years. It says that the number of transistors in an integrated circuit doubles about every 2 years. And when combined with Dennard scaling, we have been enjoying an exponential growth in the performance of general-purpose processors before 2005. But as you can see from this graph, Dennard scaling has slowed down and stopped since then. And the single-threaded performance of general-purpose CPUs hasn't been increasing. And it's unclear if the Moore's law will continue as we are reaching the physical limit of transistors. So the unfortunate takeaway is that general-purpose CPUs is not getting any faster. At the same time, network speed, particularly in data centers, has been increasing constantly. Today, 40 gigabit and 100 gigabit Ethernet are commonly deployed in large data centers, and we have 400 gigabit Ethernet already commercially available. And there is plan for terabit Ethernet in the near future. The result of the above two trends is that CPU processing is more and more becoming the performance bottleneck. To illustrate the problem, here I show you a graph of the latency between two successive packets with increasing network speed. At 100 gigabit per second, the CPU has only about 100 nanoseconds to process the packet before the next packet comes. But if you look at Linux packet processing software, that is already an order of magnitude slower than that. And if you look at 400 gigabit per second Ethernet, the CPU can do at most one DRAM access per packet. So this trend is not just in networking. CPU processing is becoming the bottleneck in many other areas in computing, including graphics processing and DNA training. To tackle this problem, hardware vendors have been producing more and more specialized accelerators like graphics processors, deep learning processors, specialized network interface cards, and reconfigurable switches. All these accelerators are specialized for a specific set of tasks, and they have much higher performance and energy efficiency than general-purpose processors. With the increasing popularity of these hardware accelerators, the time has come for us to rethink how we design system software. Traditionally, we have applications and libraries running in user space, and the operating system provides services like network stack and file systems, and as well as protections and isolations among different applications. Both the operating system and the applications run on general-purpose processors, and different machines are connected to each other through a best effort network that simply forwards and routes packets. Well, now we have all these different hardware accelerators deployed as co-processors or as peripherals or somewhere in the network or as dedicated services in data centers. So what kind of system abstractions and interfaces do we provide to applications to utilize these hardware accelerators to improve their performance. And how can we design system software to more efficiently share multiplex and protect accesses to these hardware accelerators? Today, I'll talk about 2 projects I've done on co-designing distributed systems with network hardware accelerators. Then I will briefly share with you a future work direction on hardware acceleration framework for network function virtualization. First, I'll talk about how we co-design state machine replication with programmable switches. With the increasing scale of data centers, server failures are becoming the common case, not the exception. And we have been seeing news headlines about cloud service interruptions more frequently in recent years. A common approach to deal with server failures is called state machine replication. State machine replication conceptually is very simple. It applies the same sequence of operations on multiple machines called the replicas. So even when one of the replicas fail, the remaining machines can still serve client requests. The challenge, however, is to ensure that all the replicas apply the same operations in the exact same order. To ensure these properties, the standard approach is to use a distributed algorithm like Paxos to implement state machine replication. Here I show you a protocol diagram of Paxos. The client first sends a request to a leader replica who is responsible for providing a total ordering of all requests. The leader replica then forwards the request to the other replicas. And when the leader receives enough acknowledgements, which guarantees the reliability of this request, it then executes it and replies back to the client. As you can see from this protocol diagram, the leader replica becomes a throughput bottleneck of the system because it receives many more messages than the other replicas. And these multiple rounds of communication adds substantial latency penalty to each client request. If you look at the overall system stack, traditional state machine replication protocols are completely implemented in user space. And it provides both the ordering and reliability guarantees. This traditional approach suffers lower performance because of the inefficiencies of packet processing in general-purpose processors. So the insight of our new system, called NOPaxos, is the separation of these 2 properties. And we instead implement a new network primitive that efficiently provides ordering of all messages. This co-designed approach of network and distributed system virtually eliminates all coordination overhead in state machine replication. Well, to implement this new ordering network primitive, we use a new type of network devices called reconfigurable switches. Unlike traditional fixed function ASICs, users can program the switch data plane and therefore perform simple application-specific computation at line rate. The design of our new network primitive, called the ordered unreliable multicast, is actually pretty simple. We designate one programmable switch in the network as a sequencer, which essentially provides a counter service. We configure the network to forward all client requests to the sequencer switch first, using SDN approaches like OpenFlow. Upon receiving client requests, the sequencer switch increments the counter and writes the counter value into the packet header. Using these counters, the replicas can easily determine the order of messages, and they can even detect message drops. Say message 3 to this middle replica is dropped. When it receives the next message, it quickly notices there was a message drop because of the gap in the number sequence. And we use this drop detection to implement efficient message recovery mechanism in the replication protocol. With this new network primitive, now let me show you the normal case protocol for NOPaxos when messages are not dropped. Client requests are first routed to the sequencer switch and then forwarded to all replicas. Because the network already guarantees ordering of all messages, the replicas simply execute the request and directly respond back to the client. Unlike traditional Paxos, there's no coordination among the replicas, so none of the replica will become a throughput bottleneck. Also, each client request is processed in a single round-trip time, which is the theoretical minimum. Due to time constraint, I'm not going to elaborate the protocols to handle message drops, server, or sequencer failure. But if you're interested, please check out our paper. Now let me demonstrate the performance benefits of NOPaxos. Here, I show a throughput latency graph with higher throughput to the right and lower latency to the bottom of the graph. NOPaxos is able to get 4.7 times throughput and 40% reduction in latency compared to Paxos and fast Paxos. And it outperforms a throughput-optimized version of Paxos by 25% higher in throughput and 6 times lower in latency. More importantly, NOPaxos is able to get performance virtually equivalent to an unreplicated system by eliminating coordination in the common case. Now, I will move on to a different project that uses programmable switches to improve the load balancing of distributed storage systems. Many real-life workloads are highly skewed. For example, a tweet from a celebrity like Justin Bieber attracts millions of views, retweets, and comments. But if you look at tweets from me, they basically get zero traffic. This phenomenon is actually very common in real life, and we even have a name for it called the power law. It says that a very small percentage of popular objects attract a majority of request traffic. At the same time, the set of popular objects changes rapidly as new trends rise and fall. These highly skewed workloads impose a lot of challenges to distributed storage systems. The server that unfortunately stores popular tweets from Bieber will receive way more traffic than the other servers and will quickly become overloaded. This load imbalance will lead to significant performance degradations, and requests going to these servers will suffer higher response time, and the overall system's throughput is bottlenecked by these overloaded servers. To deal with this challenge, our new system called Pegasus uses an approach called selective replication. The concept is actually pretty simple. We replicate the most popular objects onto multiple servers. Requests to these objects can then be processed by any of these servers, therefore effectively balancing load across all of them. We, however, are now facing a number of new challenges. For example, we need to keep track of the set of objects that are currently replicated, as well as the server machines that they are currently replicated on. We also need to ensure the consistency of these objects when there are concurrent reads and writes. A simple approach is to build a load balancer in software that implements all these functionalities. However, because all requests to the storage system needs to go through the load balancer, it will quickly become a bottleneck of the entire system because of the inefficiency of software packet processing. So Pegasus' solution is to instead implement all these functionalities inside the network. And to do that, we build an in-network coherence directory in the top of rack switch of a rack scale storage system. Leveraging the programmability of these switches, we store the identity of the most popular objects that are currently replicated. And for each replicated object, we also track the set of servers they are currently replicated on. All requests go through this coherence directory. And when the switch receives a request, it checks if the request is for a replicated object. If yes, it picks one of the servers from the replica set to forward the request to. A key point is that we can implement all of these coherence directory functionalities efficiently on current generation programmable switches. Due to time constraint, I'm not going into detail of our protocol to guarantee strong consistency of these replicated objects. But if you're interested, you can go check out our paper. Now let me show you some quick performance results of Pegasus. Here I show the 99th percentile latency of a distributed storage system with increasing skewness in the workload. When the workload becomes more skewed, a classical approach like consistent caching becomes less effective. The tail latency quickly deteriorates to more than 60 times the median due to the severe load imbalance in the system. Pegasus, on the other hand, is able to maintain the same level of load balance across all skewness levels, and is able to achieve a more than 30 times latency improvement over consistent hashing. We have also shown that Pegasus is able to maintain the same level of load balancing across a wide variety of workloads, including read-heavy, write-heavy, and read-write mixed workloads. Lastly, I would like to share with you some of my ongoing and future work directions on hardware acceleration framework for network function virtualization. Network functions such as firewall, load balancers, network gateways, and network address translations have been ubiquitous in today's network. Recently, there is a trend to move network functions from proprietary hardware into software instances running on commodity servers using virtualization techniques such as virtual machines and Docker containers. But the inefficiency of software packet processing means that software-based network function virtualization is not going to scale with the increase in network speed and application requirements. The problem is exacerbated by the additional software layers in the middle, like virtual machines and containers. Therefore, there is an urgent need to deploy a virtualized network function to specialized hardware accelerators. However, currently there is no unified programming framework to specify network functions to run on different hardware platforms, meaning a network function implementation needs to be completely rewritten to run on a different type of accelerator or a platform with different hardware configurations. Secondly, there's no good virtualization system for these accelerators to efficiently share multiplex and protect hardware resources among multiple network functions. So the vision of this project is to design an end-to-end language, compiler, and virtualization framework for network function virtualization. Specifically, we're going to design a target-independent high-level language for specifying a wide range of different network functions. And then we're going to build a retargetable compiler for a diverse set of hardware architectures. Lastly, we're going to build a virtualization system to efficiently run multiple network functions on this set of hardware accelerators. Due to time constraint, I'm not going to elaborate on the details of this project, but if you are interested, I'm happy to chat offline. In conclusion, with the end of Moore's law and Dennard scaling, hardware specialization is becoming an attractive solution to a lot of the problems in computing. And to that end, today I described two of my work on co-designing distributed systems with programmable network hardware, including state machine replication and load balancing in distributed storage systems. And lastly, I briefly mentioned my ongoing work on designing a portable hardware acceleration framework for network function virtualization. Thank you for your time, and I'm now happy to take questions.